In this video I'm going to talk about the Gaussian integral and how to evaluate it. So basically we have this integral from minus infinity to infinity of e to the power minus x squared dx. So we need to evaluate it. So the trick here is to start not from the integral itself, but from the square of this integral, and then to split it into two variables. So let's so of course, like when we find the square of the integral, we at the end are going to take the square root to find the original integral. But so we start with the square of the integral, and we rewrite it as a product of two same integrals. So integral from minus infinity to infinity e to the power minus x squared dx, and the same integral again. Minus x squared dx. Okay, so now we notice that like we can substitute the variable because like the definite integral doesn't depend on which variable is used, so we can, instead of x, we can write y in the second integral and keep x in the first one. So now since it's two different variables, so we can combine these two integrals together and to convert it into a double integral. So it's equal to double integral e to the power minus x squared e to the power minus y squared dx dy, and this varies basically by the whole space r squared, by the whole plane. So now we are going to substitute the variables to polar coordinates. So to convert the Cartesian coordinates to polar coordinates. So this is a kind of a standard substitution. So like I'm not going to prove everything in detail how to substitute the variables, but basically like so the variables is the substitution is like x equal to r yeah, so like we introduced two new variables, r and theta. Theta is the angle, and the substitution is written like this, and it is kind of a standard thing, so standard substitution. So we know how to rewrite dx dy. So dx dy should be rewritten as r dr d theta. So again, I'm not going to like prove this in detail because it's a standard substitution, but like it's possible to do. So now we continue the chain of equalities for the integral. So the integral is equal to oh yeah, I forgot another thing. So here we notice that this can be, okay, let's do another step. So this can be rewritten as e to the power minus x squared plus y squared dx dy. And now we do the substitution. So we see that this x squared plus y squared, this is exactly equal to r squared. Okay, so that's why it's very convenient to do the substitution to polar coordinates. So now this is equal to e to the power minus r squared, and then it goes to dx dy, which we rewrite using this formula. So this r dr d theta. Okay. So and so theta varies from 0 to 2 pi, and r varies from 0 to infinity. So now we notice that this part doesn't depend on theta, so theta basically can be split, so we can split in, the double integral again into two one-dimensional integrals. So it would be integral from 0 to 2 pi of d theta multiplied by the integral from 0 to infinity of e to the power minus r squared r dr. So the first integral is very easy to evaluate. So this is basically theta that varies from 0 to 2 pi. So it's basically, okay, let's rewrite the second one from 0 to infinity to the power r dr, and the first one, so this is equal to 2 pi minus 0, right? So it's equal to it's equal to 2 pi simply. So 2 pi from the first integral, and now in the second one we are going to make another substitution. So we introduce a new variable u, which is equal r squared, right? So then we notice that with this substitution so basically du by dr is equal to 2r, right? So then basically 2r, so basically r, this part r dr should be equal to simply du over 2. Yeah, so we write this is equal to the integral of e to the power minus u, because r squared is equal to u, minus u minus u multiplied by du over 2, right? So then we write here that this is equal to okay, so 2 and 2 cancel each other, so it remains p multiplied by pi multiplied by the integral, pi multiplied by the integral. Okay, I forgot here to write the limits, but it's still from 0 to infinity. Pi multiplied by the integral of e to the power minus u du. Okay, so like we know that definite integral, indefinite integral would be equal to minus e to the power minus u. So the indefinite integral of e to the power minus u is equal to minus e to the power minus u. Like you can verify it directly by differentiating this function. So this should be equal to pi multiplied by e to minus e minus e to the power minus u varies from 0 to infinity. So now so at 0 this, okay, let's write this in detail. Pi multiplied by, so at infinity, like for infinity we can't evaluate it directly, it should be a limit, so it's so it's a limit when u tends to infinity of minus e to the power minus u minus minus e to the power minus 0, like this. So now let's evaluate this. So minus 0 is it's the same as just 0, of course. Now e to the power 0, it's 1, so this evaluates to 1, and these two minuses, they cancel each other. Cancel each other. So basically this whole second term, it evaluates to 1. All right, so now it remains to find the limit, and so minus e to the power minus u is equal as minus e. Okay, let's write it. Minus 1 over e to the power u. Right? So when u tends to infinity, so e to the power u clearly is unbounded, so it tends to infinity as well, tends to infinity, and therefore this fraction 1 over e to the power u tends to 0. Tends to 0, and minus doesn't really change anything. So minus 1 over e to the power u tends to 0. Therefore, this limit, so this limit, first term, this limit is equal to 0. Okay, so again, the first term, this limit is equal to 0, and the second term is equal to 1. So in total we have pi multiplied by 0 plus 1, which is equal to pi. Okay, and now we recall what we were calculating. So this chain of equalities was for this integral, which is the square of the integral that we need to find. So basically the Gaussian integral, it should be the square root of what we found. So the integral from minus infinity to infinity of e to the power minus x squared dx should be equal to the square root of pi. And that is the final answer. That's it.